one announcement. Even though you will have no academic exercises Thursday and Friday, I know you'd feel a sense of shock and disruption and, dare I say, dislocation in your life if I didn't stick to schedule. So there'll be a skill testing question on Tuesday based on the homework 12. And that'll be the last one because the subsequent week is the last week of semester, and since there's a final exam in this subject, there can be no tests during the last week of class. So we will not have any weekly test. Today I want to talk about biochemistry. We're going to spend the next 3 lectures on biochemistry. This is the chemistry of living organisms. And I want to make several points by way of introduction. The first one is that living organisms are chemical systems, and they're governed by the same laws that apply to inanimate matter. We don't have a special chemistry. And in fact, I came across this comment that was made by the Nobel laureate Richard Feynman, who said that if in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? I believe that it is the atomic hypothesis, or the atomic fact, or whatever you wish to call it, that all things are made of atoms. Little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling upon being squeezed into one another. The atomic hypothesis. All right? Very important. Second comment I want to make is none of us is unaware of the boom in biotechnology today. What is the boom in biotechnology? Why do we have the boom in biotechnology? It's really a boom in biochemical technology. What's the modern biology called? It's called molecular biology. And what is the science? What is molecular science? This is chemistry. And more importantly, it is really not just chemical composition, but spatial arrangement. So chemistry, material science, solid-state chemistry underlie the boom in biotech. So that's why we're going to spend some time. We're spending 10% of our lectures in 3091 on this topic. And the last comment is, why only now? Why didn't this happen 50 years ago? What's enabling this boom today? And I think about the ages of, well, the answer is complexity. Let's get the answer out there. The answer is complexity of the chemistry. And if you think about how materials have evolved over time, you know, we date our ages. The ages of man are dated in terms of materials. We have the Stone Age, Bronze Age, Iron Age. We might call the first half of the 20th century the Plastics Age. We might call the last half of the 20th century the Silicon Age. And we see increasing complexity. To work with stone, stone is found in nature. It requires only a change of shape. But everything else, the metals, the bronze, the iron, not found in nature, native. So that requires a change in shape after a change in chemical composition. Chemistry is magic. Chemistry is magic. And chemists were revered as sorcerers, magicians. They were highly respected. Not today. There are compelling reasons to be alive today, but not for the respect given to chemists. But it's magic to take something and convert its chemical composition, and that took time to get the fires hot enough to discover the chemistry that would allow us to take a pile of sand and turn it into a semiconducting device so that you could talk on a phone or type a letter on a solid-state device known as a computer. That took time. So polymers come at the dawn of the 20th century. Macromolecules. It turns out that many of the molecules in living organisms are macromolecules, so necessarily our understanding of this chemistry had to wait for the understanding of polymer chemistry. And finally, now we have information technology. We have our understanding of macromolecules, and now we can go forward with biotechnology. So let's get down to business and start talking about the chemistry of specific biomolecules. And they fall broadly into 4 categories. So let's document the 4 categories of biomolecules. So we have, first of all, proteins, carbohydrates, nucleic acids, and lipids. And in the 3 lectures that we have, I'm going to focus primarily on proteins, nucleic acids, and lipids. And I think this will get you far enough along to enjoy subsequent chemistry. So let's get down to business and start with proteins. Proteins comes from the Greek word proteos, which means of first importance. And these are macromolecules. These are macromolecules, polymers of a sort, and they're formed by polymerization. And the mer groups that go into this macromolecule are called amino acids, formed by polymerization of amino acids. So we better get a grip on what amino acids are. As the name implies, they must be compounds that have an acid group. In other words, capability of donating protons. And amino means there must be some kind of an NH formation. So let's draw the skeletal structure of a prototypical amino acid. We start at the center with a carbon that's sp3 hybridized. And one of the terminals contains an amino group which consists of this formation bearing nitrogen. The acid is given above. This is a carboxylic acid, carbon, double bond to oxygen, and then the OH. And this H is capable of detaching. So there is the amino acid. The third bond goes to oxygen. So 3 of the 4 bonds are uniquely specified in every amino acid. 3 of the 4. And now the 4th one, this is a tetrahedron, so I'm trying to indicate that this bond is receding into the back, is variable. And I'm going to use the carrier variable R, and this is the term for the substituent. The substituent. And this is nature's choice. This is nature's choice. So, in principle, anything that will covalently bond with a sigma bond can be put here. So this means that there are thousands and thousands of compounds that qualify as amino acids, but in proteins, only 20. Only 20 found in proteins. So that's a short list. It's a rather compact library. And let's take a look at the types of substituents, and for that you can look at the table here in your reading. This is from the table, so this actually spills over 2 pages. And what we see here, I know that's very hard to read, but it's more iconic just to sort of symbolize that maybe somebody has done the reading and they say, I recognize that, I recognize that table. So there's 20 different R groups, 20 different substituents, and they themselves fall into 4 categories. So the R groups can be broken down into 4 categories. First one is nonpolar. The R group is nonpolar, and clearly under that circumstance we'd have something that is hydrophobic. Hydrophobic. Nonpolar groups would be less inclined to bond to water. We have the option of polar groups. Polar with hydrogen bonding capability. With hydrogen bonding capability. And such groups are going to be hydrophilic. There's a third group that has a net charge. So the R group is actually net positive. net positive. And so that means these are going to be strongly hydrophilic, have a very high affinity for water, and it turns out they will function as basic in aqueous solution. And then the last group is a set of substituents that have a net negative charge. And these two are strongly hydrophilic and will act acidic when dissolved in water. Now, our bodies can synthesize only 10 of the 20 amino acids. So you'll read in advertising that certain foods contain some of the essential amino acids, meaning they contain some of the 10 amino acids that we're incapable of processing. And failure to consume this in the diet over a long period of time can have deleterious effects, prompting, in the extreme, you're exiting the carbon cycle. So you do want to watch your diet. Now, there's one other structural feature that is important in the amino acids, and that I want to show with reference to a specific amino acid. So let's choose, this one's alanine. In alanine, the substituent group is methyl, CH3, so I can draw alanine as follows. Using the skeletal structure to the left, here's the amino group, which I'm just going to truncate as H2N, and maybe later I'm even going to get so bold as to put NH2, recognizing that it's not the H that's bridging to the nitrogen, but let's do it this way. The carboxylic acid will go up here, we'll go here, and then we'll just put the methyl group. Now, I could just as easily have written it the following way. I could have done this. I could have put the amino group to the right, the hydrogen to the left. Now, if you look at these two, at first glance, you might say, well, I just got to turn it, and he's basically written the same thing. But upon closer inspection, you'll discover that it's impossible to convert the one on the right to the one on the left. In fact, they're not superimposable. What we're looking at here is essentially a pair of gloves. This is considered the left hand, and this is the right hand, and you can close the gloves, you can make them fit one against the other. They will mirror one another across a mirror plane, but they're not superimposable. You know, as opposed to something like, say, propane. If I take propane, which is also carbon sp3 hybridized, propane, in contrast, has methyl above and below, and that clearly is perfectly symmetric and doesn't have such a glove-like feature. Such molecules that have, we say, a handedness are called chiral. Chiral, from the Greek word for hand. So chirality is the property of having handedness, non-superimposable. We call these, another term for these is stereoisomers. We can consider chiral molecules stereoisomers. Stereoisomers. And the different hands, if you will, the different hands are called enantiomers. Enantiomers. We don't refer to one stereoisomer, the other stereoisomer. We refer to the enantiomer, coming from the Greek word for mirror. Enantios is the Greek word for mirror. So these are different mirror images. The other thing about these is that they are optically active, and what they will do is they will take polarized light and rotate it through a degree of polarization. Here, just to give you another example of the difference between something that's chiral and not. You see the boxes at the top with no distinguishing features. They can be twisted and turned and made to superimpose over one another. By putting these little features in the bottom corner, we render these boxes chiral. And no matter how you twist and turn this box, you won't be able to superimpose it on top of the other box. Here's a more complicated molecule that can come chemically identical, but has a right-handed version and a left-handed version. So let's talk about optical activity. The only reason I refer to this is that it gives the labels that are used in referring to one versus the other. So if you have a light source that just gives light that's randomly polarized, that is to say it's not polarized, and then you put it through a polarizing prism so that the light is polarized in a certain direction. In other words, the electric vector is only in one direction. Now the polarized light, here it's indicating that it's polarized vertically. This is the optically active substance, which could include an aqueous solution of alanine. And if the aqueous solution of alanine consists of only one enantiomer, then when the polarized light passes through that solution, the plane of polarization will be rotated a certain amount by interaction of the light with the electrons in the orbitals in this particular molecule. And what you see here is an angle of rotation alpha, where alpha is proportional to the concentration of the chiral species and also the path length through the solution. So if we put in both enantiomers, we expect no change. If we put in one enantiomer, we will have one direction. And so it turns out that the different enantiomers will cause different directions of rotation, and this is how they're labeled. So the one that I've shown here on the right will cause a clockwise rotation of the light, and so it is termed D, as in dextrorotatory, from the Latin word for right, dextrorotatory. So this is the dextrorotatory form, and then the one here on the left will cause the light, and I'm going to write H nu here. It's the plane of polarization of the light that's rotating. All right, so the plane of polarization, if it went through a solution that consisted of only the enantiomer depicted on the left, it would move in the left direction. And even though the Latin word for left is sinister, they didn't call it sinistrorotatory, they call it levorotatory. I guess they had to go to the Slavic languages to get a root word. So levorotatory is this one, dextrorotatory. Some will call this the positive enantiomer, and the left one the negative enantiomer, but in most of the reading that you'll encounter, it'll be the D and the L. It turns out that only the L form of amino acids are found in proteins. Only L enantiomer of amino acids found in proteins. But synthesis could give rise to both. Synthesis could give rise to both, and certainly chemical synthesis will give rise to both. I'm not going to spend much time on carbohydrates, but just for reference, the carbohydrates are also chiral molecules, and it turns out that in sugars, only the D form is metabolized by our bodies. So you may have heard of invert sugar or baker's sugar. This is simply the L form of the various sugars, and this passes unrecognized through the body. Honey contains the L form of the carb because it's processed by bees, and the bees have a different biological apparatus. So this gives rise to, there's science fiction where somebody is after some grand event, finds themselves in a strange place it's always got to be a desert island, and they end up eating fruit that happens to be chock full of energy, but it's the wrong enantiomer, and the people, although they're filled to satiety, they die because they can't process the food. So that's the basis. That plot line has been used already, I'm sorry to tell you, so you can't use it now. Okay? And a mix, when both enantiomers are present, this is called racemic. And this is very important. I said it's a matter of life and death. It's very important in pharmaceuticals. There's a couple of, I'll tell you one example. Back in the 1960s, there was a drug that was produced by a German pharmaceutical company called thalidomide. And thalidomide was developed as an anticonvulsant, and it was also good as a sedative for people that were severely depressed. It had one of the properties of thalidomide was that you could not overdose on it. If a person took a huge quantity of thalidomide, it would make the person comatose. You'd go into a deep sleep. You'd be an extra on the set of Rip Van Winkle, but you could not kill yourself. An unintended benefit of thalidomide was discovered by pregnant women in Europe who learned that consumption of thalidomide had a tremendous palliative effect on morning sickness, particularly early in the pregnancy. So people started using it for palliative against morning sickness. This was only in Europe. The Food and Drug Administration in the United States said it hasn't been subjected to enough testing and refused to allow its importation into the United States. And there was a lot of clamoring, saying, oh, the FDA is all old-fashioned, they're in the pockets of the drug companies, they're holding up the advance of drugs and so on. You hear these charges with respect to cancer drugs and drugs in the treatment of AIDS, where people are impatient for solutions. The FDA held its ground, but much of the drug did find its way into the United States. And then shortly after its widespread consumption, it was found that this is a teratogen, and it produces hideous birth defects. And people said, what went wrong? Why did they not discover this? Was it not tested? Was it not tested on animal models? And the answer is it was tested on animal models. It turns out that all the animal models that it was tested on, those animals lacked a particular enzyme that processes thalidomide the way it's processed in humans. So this is something that caused quite a stir at the time. What's the punchline? The punchline is it's a chiral molecule. Only one enantiomer causes the birth defects, but nobody knew at the time. So if they'd known, and instead of selling a racemic form, had sold a form that has only the one enantiomer, they could have had the beneficial effects without the undesirable effects. And now thalidomide is back in the news. Some people have discovered that it may have some benefit as a component of a cocktail that's being used in the treatment of AIDS. But the memory lingers on, and there's a tremendous thing. By the way, Ritalin, which is used in the treatment of ADHD, it's also racemic, and there's some, it's chiral, forgive me. It's chiral, and it's been produced without regard to its chirality. And it's now emerging that the D enantiomer, the D form, is effective in the treatment of ADHD, and the L form is ineffective, and some of the undesirable side effects of long-term use of Ritalin may in fact be linked to the L enantiomer. So what you're seeing in more and more in drug design is attention paid to the structure. It's the structure. In fact, why don't I cut to the chase? This is what drug design is all about. This is in like 2 minutes, all right? Let's say this is some receptor molecule, and it's got little dipoles here. This is a delta minus, and this is a delta plus, and maybe this is a delta minus, and this is a delta plus just arbitrarily. And this is some candidate drug that is supposed to come up to this receptor. And the drug is designed to react. What's going on is really a lock and key mechanism, all right? And you know the Debye frequency. The Debye frequency is about 10 trillion hertz. 10 trillion times a second, nature puts the system to the test. 10 trillion times a second. So on one of those tests, suppose this drug that's supposed to bind to this receptor, where this is delta minus, this is delta plus, where this is delta plus, this is delta minus, and so on, then the two will stay together long enough to do the math and figure out that there's some more energy to be gained through a further chemical reaction. If, on the other hand, this is somehow misformed so that opposite this delta minus is also a delta minus, during that collision, there won't be that staying power to keep things together long enough, and so the activation will not be achieved, and so the reaction won't go forth. So really, the message here is that atomic arrangement is the key. With a pun here, it's the key. You know, this is a lock and key mechanism, and atomic arrangement is the key. Paying attention to chirality. Of course, the other thing is, let's understand the chemistry to such a high degree that we're not relying on field testing to sort of determine whether something's acceptable or not. We need to get rid of determinism, get rid of empiricism and ramp up the determinism. All right, let's talk about properties of amino acids. What are the properties of these compounds? Well, first of all, they're solids. They're solids. Solids at room temperature. And they can crystallize. They can be crystalline. Remember, these are the mer groups. They're not the polymers. These are the mer groups that have yet to be polymerized. They can crystallize. I think it's fair to say they're going to be colorless, entirely covalent, highly bonded, and they're moderately soluble in water. Moderately soluble in water, which is a good thing for something that's going to function as a biomolecule. I think solubility in water is desirable. And in fact, I want to look a little more closely at the behavior in water. And to mention that the first thing that happens, this thing transforms, and in the chart that's in the book, that bio table 1, you don't see the amino acids drawn as I've drawn them, with the amino N neutral and the carboxylic N neutral. They draw them as follows. They show what happens when the amino acid has already been dissolved in water. So let's represent that solvation reaction. So I'm going to compact the notation. So here's the central carbon, there's the hydrogen, there's the amino substituent on the bottom, and on the top I'm going to put the carboxylic acid. And let's ask what happens when this dissolves in water at neutral pH. And this doesn't necessarily mean pH equals 7. It means neutral with respect to this reaction that we're going to show. What happens when this species dissolves in water is the proton leaves the carboxylic acid and comes over and attaches to the amino N. I mean, look at the amino N. This is really a Bronsted base, isn't it? This is a Bronsted base. This is an Arrhenius acid. It's also a Bronsted acid. So now we have, from what is a neutral molecule, something that looks like this. Protons attached here, rendering this N positive. The R group remains unchanged, and the carboxylic acid is now minus the proton. So this molecule, it's still net neutral because I've got charge neutrality to maintain. All I've done is relocate something within the molecule, but it's bipolar, isn't it? It's bipolar. That is to say, it's locally positive and locally negative, but globally it is net neutral. So it's kind of a strange ion, isn't it? Is it an ion or is it not an ion? Well, it's net neutral, so we wouldn't call it an ion. It's some kind of, instead of an ion, it's called a Zwitterion. A Zwitterion, which means a double ion. It's a Zwitterion or a double ion, some kind of a hybrid. So that's really important chemistry, because that gives this molecule the ability to respond to its environment. See, somehow through the chemistry, we have to explain how matter becomes animate. How matter becomes animate. What's the chemistry here? I mean, how do I do this? How do I move my hand? How do I do this? This is all macromolecular. So what am I doing when I move my hand? I'm changing the conformation of those polymers. Those polymers are changing shape. Remember the C17H36? I showed you two long chains. One was relatively straight and one was coiled. And I can go from one conformation to the other. Now, how do I do that? The electrical engineers are going to say, it's all electrical. I say, no, it's not electrical. You can't do this electrically. Where's the wires? This is chemical. It's all chemical. And I'm going to show you how. And you say, but you can't do it that fast. Fast is fast only in the mind of the beholder. This simply has to happen at a rate that is keeping pace with the conversation. On a geological time scale, this is a vanishingly short period of time, right? But otherwise, this is, as long as our data rate of understanding can keep pace with the ability for us to change the conformation, we live. So let's look at how this responds. Suppose this is, I don't know, in the wall of the stomach, and you get a hankering for some cola beverage, and you drink the cola. The cola is low pH, right? It's about pH 3, phosphoric acid, benzoic acid. So what's going to happen is this Zwitterion will respond in a defensive manner. There's a principle that's in chemistry that's analogous to a Newton's third law, you know, action-reaction. It's called the Le Chatelier principle. The Le Chatelier principle, after the French scientist who enunciated it, Le Chatelier principle. And it talks about the restorative force exerted by a chemical system. Restorative force exerted by a chemical system. And what is this restorative force designed to do? It's designed to minimize the impact of any perturbation. Designed to minimize impact or the effect of any perturbation. By perturbation, I mean not a physical perturbation, I mean a chemical shift, any kind of chemical perturbation. So, let's say we have the Zwitterions sitting happily in a neutral solution, and suddenly the pH drops. Suddenly the pH drops. So, how can the Zwitterion respond? What do I do to bring the pH back to where it was before the disturbance? What is the manifestation of pH? It's proton. So somehow the proton concentration suddenly went way up, driving the pH way down. And I'm Zwitterion sitting here. Here's Zwitterion right here. What could Zwitterion do to minimize the impact of this flood of proton? Well, it's got two possibilities. How do you neutralize something? You either flood this with hydroxyl, all right? Start flooding this with hydroxyl in order to neutralize. I look on Zwitterion, I see no hydroxyl, so that's no good. But what could Zwitterion do? There's, at the carboxylic acid end, an attachment site for proton. So what Zwitterion can do is to gobble up the excess proton in order to bring the pH back to where it was before. So let's write that reaction. It triggers this response, which is, here's the amino end. I'm going to put the carboxylic acid over to the right here. So now this is from the solution. This is from the solution. It's trying to bring the pH back to where it was before, consuming the proton and attaching the proton to this carboxylic acid end. So what's happened now to Zwitterion? This end, the negative end, has been capped. So Zwitterion now is net positive. It's net positive now. Over here, it's net neutral. And it's gobbling up protons from the solution. And so this is really an acid-base reaction for which I can write a K, an acid dissociation constant. And, you know, I'm getting tired writing all these characters, so I'm going to reformat this. So I'm going to say this is the Zwitterion is, I'm going to represent as proton plus the rest. And this is proton. And what's this thing here? This is now Zwitterion to which proton has attached. I've attached this proton to the net neutral species. Okay? So I can rewrite this reaction in a more compact notation. So A captures all of this other stuff minus the proton. So I can write the K for that reaction, and K1 will equal the concentration of proton times the concentration of neutral Zwitterion over the concentration of this protonated Zwitterion, the Zwitterion onto which we've glommed this proton from the solution. And we're going to take a page out of Sorensen's book, and we'll take the log of both sides, and then we can say that pK1 is equal to pH plus log. And I'm writing 10 here, but you know, in engineering, if you see log, it's typically log base 10. I know in some of the math classes they use the log to represent natural log, but it's uncommon in engineering. All right, so here's the Sorensen version of the equation. And what this tells us is that at 50% association, in other words, when 50% of the Zwitterion has gobbled up the proton to generate this protonated species, this ratio is equal. 50% Zwitterion unprotonated, 50% protonated, so the log of 1 is 0, and that's the pH that gives us the value of the acid dissociation constant at 50% of consumption of Zwitterion. We have the concentration of Zwitterion equaling the concentration of the protonated Zwitterion, and therefore the pH is exactly at the value of pK1. Now what happens on the other extreme? What happens if all of a sudden there's a rise in pH? If there's a sudden rise in pH, how does Zwitterion respond? Sudden rise in pH, that means the concentration of proton suddenly fell. So we use the Le Chatelier principle again. We use Le Chatelier principle. We go back over here and we look at Zwitterion and we say, okay, what we've got right now is a sudden dearth of, a shortage of proton. How can Zwitterion respond to that sudden shortage of proton? Well, the neutral Zwitterion has protons sitting right here. So what Zwitterion can do in response to that sudden drop in proton concentration is donate, become a proton donor, and start adding protons to the solution, sacrificing its neutrality in order to minimize the impact of that sudden rise in pH. So let's document that reaction. That's this one here. That's where Zwitterion does the following. We'll start with the neutral again. So that's over here, H3N. So here's the neutral Zwitterion, experiences a sudden rise in pH and responds by dumping protons into the solution. So now the left end is deprotonated, leaving it neutral. And this proton is now donated to the solution, and if this solution is in fact high in pH, then this proton can go and attack the excess hydroxyl and neutralize it. So this is how Zwitterion responds. And what do we see here? This is neutral. This is net neutral. But now the positive end has become neutralized by the loss of the proton. So this is now net negative. This is now net negative. And so we can call this reaction 2, and it has a K2. And using the notation that I've developed up there, the neutral Zwitterion I'm denoting HA. So this is the Zwitterion minus this proton. So this is just the A minus. It's making sense. This is net negative, and if I take H away from HA, I get minus, and then this is the H plus. So that's the reaction we're looking at, and we can write the K for that reaction as concentration of proton times concentration of deprotonated Zwitterion divided by the concentration of the neutral Zwitterion, and take the log base 10 of both sides. pK2 is pH plus log base 10 of, I'm going to flip this over so I don't have to put a minus sign here. So this will be HA divided by A minus. And again, when we have 50% neutralization, then that means that there'll be 50% of this species consumed, 50% of this left. The log of 1 is 0, and at that pH we have the value of the acid dissociation constant. And I think this slide shows what's going on here. All it does is it plots these two equations. If you take the first equation here, the logarithmic, the Sorensen form of the first equation, that's the lower part of this graph. The lower part of this graph, we're plotting pH versus the ion dissociation. So if you turn this around, pH versus the amount of this that has been consumed. And what you see is that when you have 50%, this is 50% ions dissociated per molecule. At 50%, we have the pK1, where both are equal. The other thing to note is that as this reaction is taking place, look at the gentle change in pH. The concentration here changes from, roughly about 10% up to 90%. So we have an 80% variation in concentration. By that I mean an 80% interval over which we are changing the amount of attachment here. Here there's no attachment, here there's total attachment. And in the middle we have from about 10% to 90% attachment, the pH only moves about 2 units. So Zwitterion is fighting really, really hard to get this pH up to a certain level and hold it there. So we say that the Zwitterion, under these circumstances, is acting as a buffer. So Zwitterion acts as a buffer. So what it will do, it's got the capacity to either donate protons or remove protons, and do so in a way that reduces the impact of the pH. And then here's the other part of the graph, which is up the upper part, the case where we have a sudden rise in pH. So the pH goes up, and Zwitterion is now holding the pH as best it can around a value of pK2. And so then there's a special point on this graph, and it's shown right here, where we have maximum undissociated Zwitterion. In other words, what is the pH at which we have 100% undissociated Zwitterion, okay? Just the Zwitterion. And that's given by the balance between the K1 and the K2, and that's called the isoelectric point. Isoelectric point, because then everything is net neutral. Isoelectric point, and that's also given the notation PI, lowercase p, capital I for isoelectric, and in this case it's simply the average of pK1 and pK2. Average of pK1 and pK2. And this can be found for various amino acids. I don't expect you to know the amino acid compositions by heart. I would always give you the chemical formula of the amino acid, and if you had to do anything with such calculations, I tell you what the K1 or the K2 is, as the case may be. There's one other twist on this. There are a few amino acids where the R groups are also capable of attaching or donating protons. We say that the R groups are titratable. R groups are titratable. That is to say, they can also be proton active and can participate in this Le Chatelier principle in action. And if you look on the homework, question 11 on the homework goes through an analysis of how you deal with a situation where there's a change in pH, and for example, suppose you've got a side group. Aspartic acid is a good example. in aspartic acid, the R group is methylene, and then there's a carboxylic acid sticking off. This is the R group. Well, clearly this is a site of attachment. So if I get a sudden drop in pH, there's a flood of hydrogen ions. The hydrogen ions can be attaching not only to the carboxylic acid end here, but they can also be attaching on the R group. So that brings a new level of complexity, and we work that out in the particular homework example. Okay, well, let's take a break here now, and I'll leave you with 5 minutes on extreme kinetics. Earlier in the semester, I went up to Halifax to give a seminar, and I was reminded of this, which actually our audiovisual technician, Dave Broderick, had brought to my attention a number of years ago. We talked about the extremes in kinetics, one of them being an explosion. The reason I tell you about this, it follows kinetics, and also it's apropos of the season. After Thanksgiving Day, when you go downtown, you will see a feature that I'm going to tell you about at the end of this story. On December 6, 1917, this was in the middle of World War I, and Canada was part of the British Empire at the time and was drawn into the war. Halifax was a port of exchange of a lot of munitions. So there was the Belgian relief ship, the Amino, and the French supply ship, the Mont Blanc, and this is the cargo of the Mont Blanc. And you can see it was a potent cargo, to be sure. At 8:45 a.m., there was a collision. The Amino hit the Mont Blanc. It missed the TNT. There's 20,000 tons of it. But it struck the picric acid, which was stored directly beneath the drums of benzol, and there were some sparks. And so that's the way the story begins. And for this one in this light, I think I'll put on some glasses so that I can read it to you in modern English. The crew of the Mont Blanc, aware of their cargo, immediately took to the lifeboats, screaming warnings that no one heeded. They rowed for Dartmouth, which is across the harbor. The Mont Blanc drifted by Halifax Pier, brushing it and setting it ablaze. Members of the Halifax Fire Department responded quickly and were positioning their engine up to the nearest hydrant when the Mont Blanc disintegrated in a blinding white flash, creating the biggest man-made explosion before the nuclear age. It was 9:05 a.m. Over 1,900 people were killed immediately. Within a year, the figure had climbed to well over 2,000, 9,000 more injured, many permanently, 325 acres, almost all of North End Halifax, destroyed. And much of what was not immediately leveled burned to the ground, aided by winter stockpiles of coal in cellars. As for the Mont Blanc, all 3,000 tons of her were shattered into little pieces that were blasted far and wide. The barrel of one of her cannons landed 3.5 miles away. Part of her anchor shank, weighing over half a ton, flew 2 miles in the opposite direction. Windows shattered 50 miles away. And the shock wave was felt even in Sydney, Cape Breton, 270 miles northeast. There was about 20 minutes between the collision and the explosion. It was enough time for spectators, including many children, to run to the waterfront to watch the ship burning, thus coming into close range. It was enough time for others to gather at windows, and thus an exceptionally large number of people were injured by flying glass. Many sustained permanent eye damage. Not surprisingly, hospitals were unable to cope with so many wounded, and this was also, the misery was compounded by a blizzard that struck the city the following day, dumping 16 inches of snow over the ruins of their sooty, oily covering. With astounding speed, relief efforts were set into motion. Money poured in from as far away as China and New Zealand. The Canadian government gave blah, 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 so much money, but most Haligonians, that's what you call a resident of Halifax, most Haligonians remember the generosity of the state of Massachusetts, which donated $750,000 in money and goods and gave unstintingly in volunteer assistance to the Massachusetts Halifax Relief Committee. People from the hospitals, Mass Eye and Ear, went up because so many people had sustained eye damage. And they got on trains and they went up there to minister to these people. To this day, Halifax sends an annual Christmas tree to the city of Boston in gratitude. So when you go downtown, I don't know where it is now. It used to be in front of the Prue, but I heard recently they relocated it to the Boston Common. If you see a 45-foot Christmas tree that looks like it came from Canada? That's the reason. Okay, have a happy Thanksgiving. I'll see you next week.